Alrighty, so for your programming test number 1, the results, because we have one more test session tomorrow morning. After that, I'll gather with the TA as soon as we can. And then I know that next Friday, March 14th, will be the drop deadline. Hopefully nobody drop, but that's the day we are aiming to really return the result back to you. Get the feedback, and also you get a result as well. Okay, I'll keep you posted. And the makeup lecture for the missed last Thursday class, ADT stacks been posted since last Thursday. You can check it out. And I will see if time permits, I might do one example in stack. If no, that's okay. We can do it on Thursday. So your written test, that's going to be section specific. The guide and the example questions, I'll release them maybe tomorrow, so you can get prepared earlier. But what we're going to cover until Thursday, it will be included as well. So you definitely want to go over all the lecture material, right? You got about a week, more than a week from now to get prepared. And your assignment number 3, which will be about the link trees. That assignment is not really covered per se by the written test, but you should definitely get started as well. That one there is going to be it's going to be covered by your last programming test. Also is coming, right? So just make sure you plan accordingly, right? Everything is on schedule. We are trying to follow. And my office hour, TA contact, lecture notes template, everything consistent, right? Nothing changed. Any question about the course? All right. So let's now do a very quick recap, and then we'll move on to trees. So let's see where we are. All right, let's see here. So last time we actually started about the ideas of tree. Of course, there's a summary table about doubly linked list, but you will take a look to see the detailed discussion. And then we talk about there's a roadmap for the trees that we're going to cover, but let's now just see the detail. Okay. So last time we actually spoke about linear versus nonlinear. Just got to remember, unique successor and also unique predecessor are the keys to really define whether a structure should be linear versus nonlinear. You can look back to the discussion for example. So these are all the structures that we have talked about so far, and we just introduced the trees from last time, last Tuesday actually. All right, so we talk about the different terminology for the trees. So we got root, we got parents, we got children, ancestor, descendant, sibling, right? You can revisit those concepts also with the example, okay? And then the most important concept is really about subtree, okay? So once you receive assignment number 3 tomorrow, and the assignment, each task will be supposed to be done recursively. So you just gotta make sure every time you kind of stuck, you really want to think recursively on the tree. And subtree is really the key. We're going to go over some simple algorithm on the trees today, just to get you a little bit more prepared for the assignment. Of course, you got to start early and make sure you kind of struggle through the problems. That's really the best way to learn. But of course, reach out to me if you got any trouble. But subtree, right? Very important. And then this is some problem that we spoke about last time about how you can count the number of nodes recursively, right? I think I'm going to do it once more, but more on the context of binary tree. Okay, just a revisit idea. Okay, and then okay, that's about a count recursively, and then about the number of subtrees, right? You just count the number of nodes, basically. Every node in the tree can be the root of some subtree, basically. Just count the number of nodes. And then we got external nodes, internal nodes, right? If you got any nodes that has at least one child, that will be internal nodes. If you got any node that has no children, in that case, you'll be external nodes. External nodes will be very important base cases that tells you your recursion should really start returning from that point. It will guarantee termination. On the other hand, internal nodes will be the problem being too big for me to solve right away. I have to somehow delegate to different sub-problems, right? That's something we'll keep emphasizing as we talk more problems of the trees. All right, and then let's see. We got to talk about edge, path, easy, and we'll talk about depth and also heights, right? For now, I'm going to assume that you guys know about the definition for the depth and also heights, because today we're going to see how we can calculate them in Java recursively. I'm going to do some tracing also together with you, okay? But just remember, you can divide any given tree in different levels. You start from level 0, and think about the 0 here simply means the node here has depth 0. Meaning that it takes no edges to really get to the root itself. That's why it's 0. And then for these two nodes, for example, it takes one edge to go to the root. So that's why the depth should be 1. Right? That's the best way to understand conceptually. And whenever you talk about the depth, it's really to do with a particular node. You don't really say the depth of a tree. You don't say that. On the other hand, what you can say about a particular tree would be the heights. And now watch out over here. You can say the heights of this particular tree, which will be some number. You can also say the heights of this particular smaller subtree. That will be another number, right? So I can say the heights of any arbitrary subtree that I can derive from the original tree. And the two examples we did over here just illustrate that. So I said if I want to calculate the heights of the subtree rooted at David, so I'm really considering this one here. Conceptually, you just got to divide the nodes into different levels over here. By definition, the heights will be the maximum depth of all the children, of all the descendants, basically. So you can see, as far as this particular subtree is concerned, the maximum depth is actually 3. So the height should be 3. On the other hand, I may ask about what's the heights of this particular subtree. In that case, I can disregard all the other nodes in the original tree. Don't get confused. So now if I'm focusing on this particular subtree here, I can divide the levels also accordingly. Level 0 and level 1, right? And by definition, what's the maximum depth for all the descendants? Well, right here, right? Maximum value will be 1. So that's why the height of this particular subtree will be just 1. The way I show you the definition for the depth and also for the heights are not strictly recursive, just for you to get an intuition, right? If you give us an example, you can always just divide the trees in different levels and try to see what's the depth and also the heights accordingly. But today, once we introduce you again the Java classes and some useful methods, we're going to see how we can compute the depth and heights recursively. So those are the two first algorithms we're going to talk about. Okay. All right. And for this one here, I'll just revisit in just one moment. All right. Any questions so far about what we spoke about last time? All right, so let's now continue. And let me just do a very quick recap about what a tree is. You really want to think about the tree definition recursively. So if you look at the slides, slide number 10. So the definition here kind of shows you about a recursive definition. I'll show you where the recursion comes from. When we talk about recursive definition, that means some pattern is going to recur, is going to keep happening at different subtree, right? So that's something you want to focus on. All right, let's talk about different cases for tree. Okay? And later today, we're going to talk about binary tree. It's going to be defined in a very similar way. Okay. So what will be the simplest case for a tree? Well, like for linked list, what will be the simplest case? When it is empty. There's no node. So case number 0. Oops, too thick. So case 0, we'll say empty tree. When there is no node in the tree, case 0. And then conceptually, you can think about it's like an empty set. There's no node, right, conceptually. Programmatically, you can think about you always got the root attributes in your tree class. And in this case, there's no node. So that means the root attributes will simply point to just null. Doesn't exist. You might have another attribute. Let's say we are trading space for time. And in that way, size would just be equal to 0. Right? So these are the simple properties you can imagine for case number 0, which is very straightforward. But empty tree can nicely be base cases when you try to define recursive algorithm on your tree, right? As we'll see later. All right, let's see another case. What about something almost as simple as empty tree? Let's say the tree has only one node, right? So I can say here, let's say case 1. Let's say you got what we call a singleton tree. Like when you, maybe in Math 1019, you say a set containing only one element is called a singleton set. So here we're just borrowing that term with a singleton tree. A singleton tree. That means it's a tree with just a single node. In that case, the root should be the only node, really, right? The root is no longer null. So you would say the root should be pointing to some object over here. And we'll elaborate the structure of the object a little bit later once we see the Java classes. But I just want to point out one thing here that's important, right? So when you think about the root, well, actually for every tree node, the way to really make it recursive is to really have the list of children, basically, well, like a child nodes. If you go back to, let's say, this example over here, very quickly, right? Let's say as far as this node is concerned, the way for the tree to go on with its growth is by considering the nodes at the next level. So these are the children of this particular node. And also for this subtree to really grow further, these are the nodes of its children. So the pattern is simply going to recur and also going to just repeat. That's where the recursive definition comes from. Right? That's something you want to keep in mind. All right, let's go back here. Let's draw as simple as possible. So let's say we got some attribute here. Let me say C here, standing for children. Okay, and there might be some other attributes you may have. Right? I'll just say dot dot dot. Okay, and for the children here, let's say singleton tree. So the root should have no children. So there are different ways you can express this. Okay, you can say the children is simply maybe pointing to null, for example. Right? In that way, if root the children equals null, that means the root has no children. There's a single node there. Another way you can also try, for example, you can say the children may be pointing to some empty collection. Let's say if you decide to use an array list, let's say, maybe may not be allowed for your programming test, but let's say you're developing your own projects. In this case, you might say the array list is going to store the children for this particular node. I can just make the array list empty to really represent like an empty child list. That's also possible. So this one here, for example, it would be, for example, empty array list of tree nodes. Whether you go for this option here or you go for this option here, it's more like an implementation decision you have to make by yourself. As long as you can justify the decision and make sure you stick to it consistently, it doesn't matter. Okay, so this is more like an implementation decision. Okay. Okay, we'll get more to there. All right, what about the next case? So let's say the tree is not empty and also tree has more than one node. In that way, the problem might be a little bit too big for me to solve right away. So now we got to see a little bit more about recursive structure. And we want to see where the pattern of what a tree looks like is going to repeat itself. That's where the recursive definition comes from. So I'm going to say case number 2 here. That means we have more than one nodes in the tree. Okay, more than one nodes. Let's try to visualize this, but we'll see that again when we see the Java classes. Think about we got a root over here. It definitely exists. It's going to point to some node, and one of the attributes for the object is children, right? For now, let's say the children is stored in an array. That's the example we're going to discuss in the class. However, in your assignment that's going to be released tomorrow, children is going to be stored in a singly linked list. Okay, that's something you will see later. So now for children here, it's an attribute which will just point to the beginning of some array. Of course, when you first create a child list, you will have to fix the size, right? So let's say it could be maybe index 0, index 1, index 2, maybe all the way to, maybe you can define some constant to say maximum number of children, let's say, right? Or you can just make it a magic number 10. It's up to you. All right, let's see where the pattern is going to repeat itself. The way we declare the child or the children list is something like this. Think about this node here has the type tree node, which we'll see later. Let's not worry about generics just yet. Okay, let's be a little bit more conceptual. Let's say this node here is of type tree node. What about the children list? That one there is actually going to be declared as also tree node, but it's going to be an array. All right, right here. That means every element over here in the array, if not null, is going to be a tree node itself. Basically, each node there is going to have the same structure as their parents. That's how we recur the pattern about the tree nodes. All right, let me just draw that quickly. So you can think about, let's say, for element 0, index 0 is going to point to some tree nodes right here. So this is going to be a tree node, the same type as its parents. And at index 1, let's say we have another tree node right here. Let's say the first child and the second child. You might get more children in a general tree, right? So both of them are actually tree node. And what we're going to see later is, for each one of them, they are simply also going to have their child list right here. And each one of them is just going to expand, right? Like say an array here and also an array here. So you can see where the pattern is repeating. This pattern here for the parents is repeated one here and also one here for each child, right? Right, the node and also the child list. This is why we say the structure is recursive. To draw it more generally, you can think about here, starting from here, this is the subtree rooted at the first child. I'll write it down in just one moment. And this is another subtree over here, okay? So can you think about this is the subtree rooted at the first child. And this is the subtree rooted at the second child. All right. And let me just make it even more explicit. You can think about here, the pattern right here is being repeated, number 1 to here, and also number 2 to here. So this is why we say that the tree structure here is really recursive. Once we get to the binary tree, it's the same case, really. It's just that in the binary tree case, we just restrict the number of children at every level to be maximum 2. That's the only difference. But in the general tree, if you can understand it, you should have no problem understanding the binary tree. Okay, so what I will do is I'm just going to write here. So here, and also here, and also here. So this is the recursive structure of the tree. All right, so when you review this notes here for your written test, the most important message you want to get from this conceptual sketch is about, number 1, the 2 base cases for a general tree. Number 2, why is a tree in general recursive, right? So that's really the lesson you want to pick up. All right, question? All right, sounds good. Let's now move on. The next one will be, some very quick clarification about terminology. Okay, let's go back to the slides. So slide number 10, just about what I just illustrated about recursive definition. You can take a look. There might be some additional details you can also pick up from there. All right. Okay, and then this one here, just showing to you, right, about the tree. The important thing is there should be a single unique parent path or ancestor path from the root. Oh, sorry, not ancestor path. For every node, there should be a unique ancestor path for you to go all the way to the parents. Similarly, for every node, you should only get one way to go to, there's only one path to go to another node. For example, if you look at this tree over here, right here, you can see in order to go from here to here, there are more than one path for me to go there. So I can either go for the left or I can go for the right. So this tells you it's not a tree, it's more like a graph, which you will learn about in 3101 later. All right, so this here, just want to talk about what would be the legal versus illegal organization for the tree. Okay, and let's clarify some very quick terminology. So there is this difference between ordered tree and also unordered tree. It's really about the children, really. Okay, let's say a very typical example would be about a book, right? So let's say this will be the top level, the root. And then if you look at the first level, level 1. So these are the children for the top level book. You got preface, you got part 1, part B, sorry, part A, part B references, right? So here, if you believe the order in which the children of a node matters. In this case, yes, because you should really read part A before part B, right? They kind of this maybe some logical order between them. In that way, it's called order tree. Okay. So that means there is a linear order, right? Linear in the sense that so there's only one predecessor, so there's only one unique successor from preface to, which is part A, right? There's also one predecessor from part A, go back to preface, something like that, okay? There's a linear logical order between a node's children. On the other hand, if you say a tree is unordered, that simply means there's no logical order. You shouldn't really care too much about the order, right? One example could be, let's say if you go to the REST server, if you simply say, oh, there's a command you can try. I'm not sure if you ever try. If you go to your REST server, right, log in with your account, and then go to some particular directory. Don't do that at the top level. You're going to be overwhelmed by all the details. There's a command called tree in Linux. Give it a try. And then once you go to a particular directory that you want to see what's its tree structure, you can say tree, and then you can say dot, the current directory, right? You can try that out. That will show you the tree structure. But normally we say that in Linux, between the files and the directory names, there's no logical order. Maybe alphabetical order, but it's not really logical, right? Just about alphabetical. So just one example. So we might say between these two directories, there's really no logical order. Doesn't matter if you try to go to process one before the other or after the other. Doesn't really matter. Okay. Yeah, you just got to keep in mind what's the definition for order versus unorder, and then when you deal with your application, you can just process accordingly. Okay. And of course, if you got unordered, let's say, if you got unordered trees, in that case, the children may not necessarily be stored in a array list or linear structure. It may be stored in, for example, like a hash set, for example, right? Because there's no ordering between the nodes. That's just one example. For example, you can still use a list if you want to. I'm just saying you can use, for example, you can use an array list, which is linear. You can also use maybe a hash set. On the other hand, let's say for the order tree, you should only use a linear structure. If you use a hash set, it wouldn't make sense because you already disregard the ordering. But for the assignments, you have to use a linear structure. You don't use a hash set. All right. All right. Very quick mention about this distinction here. All right. So let's now talk about how we can implement a tree in Java. Okay. Let's now talk about it. Okay, order tree, unordered tree, I just spoke about. And we had some very quick glance about the tree, this class here, but I was definitely in a little bit rush. Let me redo it again, okay, for today. And then we're going to see some simple algorithm and see how we can construct a tree. It's going to be all relevant to how you're going to do the assignments. Okay, let's now talk about it. Let's start with a single important class we called tree. Tree node, right here. First of all, you can see we got some recursive structure because we got tree node right here. You can see we got tree node here. And by the way, it's generic, right? Which you should really know for the written test as well. So we got tree node here, and also you can see we got the children, both the parents and also the children, right? You can see the children over here is an array. That tells you may have more than one children. But here, you got only a single parents. All right. One thing, something to note. And also, we have some special counter over here to really keep track of how many children we actually got for this particular node. Okay. So this is like a counter. And we say that the maximum number of children, we can define that using a constant right here. I just say 10, just for now. All right. So you can think about, for example, at a runtime, a tree node is going to look like this. I can instantiate a parameter to be a string, or it can be integer, can be person, can be whatever you like, okay? And we got parents, we got elements, the data, and also we got children. Okay, just before that, let me also highlight the data. So you can see here, we got E here, corresponding to the E, right? That's the element. So these are the three main attributes we have over here. And in the case of the array, I'll leave it to you guys to really understand this implementation. Very basic pattern from maybe 2030, 1022, 1021, from that previous Java courses. Here, we say that the array over here is size 10. That means we can store up to 10 nodes as a children. On the other hand, maybe at a runtime, you don't necessarily fill out the array at one go. Not really. So for example, you might have maybe only one child here, you got another child over here. In that case, the number of children should be only 2 rather than 10, right? So that's really the distinction you have to make, okay? So let me just write it down very quickly. At a runtime, you might have, for example, one tree node over here. You got another tree node over here, okay? So in that case, the number of children counter should be actually 2, right? So that one should be always smaller than or equal to the maximum size, right? So you will see that in some algorithm that we're going to talk about, you may actually want to use the NOC counter as opposed to just the length of the array, all right? So what you really got to look into yourself is to look at, when you look at, let's say we got some n over here, right? If you say n dot children dot length versus if you say n dot NOC, so they are really different, right? So this one here is always 10 that you set, always 10. On the other hand, if you look at n dot NOC, that should be less than or equal to 10, right? That's really something you want to watch out for, all right? Okay, and then let's see. I'm going to talk about this crazy line, which I kind of mentioned to you yesterday, right? I want to address that more properly in the next page, okay? Just give me a moment. Let's look at the method very quickly. So you got some standard accessor. You can get a parent, you can get a children, you can also get an element. You can also set each of the attribute as well. And so this is something you can also try. How do you remove a children at a particular index? That's pretty much like a remove something from the array, which we know is linear time, right? That's something you can try as well. So a little bit reflection for you to really think about. Compare doubly linked node, in which case you got previous reference, you got next reference. Against, we got parents, and we also got children, right? Think about it, how they are different. Okay, just one more thing. And here we got another, so parent is just going to point to another tree node, right? I'm going to make this a little bit more precise a little bit later. Now, I want to talk about this line here. All right, this line. And this has to do also with what you learned about in the pre-recorded lecture about generic stack. So I'm going to put all these together and talk about it at once. It's going to be very useful for you also to know which one to use really. Okay, let's now take a look. Okay, let me switch the page to right here. Okay. In the pre-recorded lecture, you got array stack, right? If you haven't seen this before, you better catch up, right, before Thursday. So we got array stack itself is generic. And we have some generic array to say the data, the type is going to be instantiated to maybe string as soon as we instantiate E to be a string, right? And so just E here. And then in the pre-recorded lecture, we show you a line about how you can initialize the array right here, right? You might be thinking intuitively, which I will tend to agree. Let me just summarize this once more, okay? Intuitively, you might be thinking, how do I initialize the array? I might say data is simply new, and then I would say E here, and then I might give some size, for example, 10. This might be the most intuitive line you might write, because from the previous Java course, if there's a string, you put a string in place of E. If there's a person, you put in person in place of E. Right? However, it's not going to work in Java. No. Okay? It's not going to work. What you got to do instead is, the very short reason is, generics is not part of the initial Java design. They only introduce it in the later version of Java. So somehow, because of the legacy they actually have, they couldn't really make it work in the most intuitive sense. That's all you got to know. Like, for now, I'm going to talk about the workaround, which is going to get more and more ugly. All right? Now, at this point, how can I do it? This one is not too bad. And you guys learned about casting, right, from 2030. Okay? In order for me to get this line to work, I'm going to say data over here will be assigned to, first of all, let me create the most general array, which would be objects. I'm going to say new objects over here, and then of size 10. And then I'm going to cast that into the generic type I want. This is going to work. All right? So whenever you got maybe an array whose type is simply a generic parameter E, in that way, all you got to do is create an array of the most general type objects, which will be at the top of the inheritance hierarchy, and then cast that into E. This is going to work. All right? Good. That's a simple case which you will learn from the pre-recorded lecture. But for tree, it's going to be very ugly. Okay, that's why I want to show you this line. In the case of the tree, you can see that just compare these two. Okay, the easiest way for you to remind you why they're different. If you look at here, the E is by itself right here. But if you look at here, the E is wrapped around by the tree node class. That's really the difference, right? Other than that, you can see you got array here, you got array here. They're the same. But the type of the array is different. The type of the array here is simply just E. But the type of the array here is the tree node of E. So you got one extra layer wrapping it. So whatever that worked before is not going to work anymore. So we need a more general solution, right? That's the brief lesson. But I'm going to show you exactly how to understand that. So this line here basically tells you the generic parameter E is wrap within the tree node class. That means if you try the solution that used to work before, let's try that. If I simply say, if I try what I said earlier, if I say the children will be equal to, so let's now do the casting. For example, if I say, I'll just TN, tree node of E, and then I would say new object array 10. Right? If you do that, like how I said it earlier, it's not going to work because now E is wrapped within another layer. So it's not going to work. Now, let's see what's the most general solution. The most general solution is you have to use a library class called the arrays. All right, going to use that class. That's what you will see in here. Okay, I'm going to write that line and then try to explain to you what it is supposed to be. It's really doing the same thing, but it's just an ugly workaround you have to know if you program in Java, right? If you go to another language, maybe you're fine with writing something that's intuitive, but in Java, we're sticking to this. Okay? Let's now write it down here. So the correct solution for this is we have to say children right here. And then eventually we still want to do some casting. Okay? Casting still is necessary. Okay? So let me still put a casting right here. So you still have to cast something into the tree node of generic parameter E. However, what's going to be on the right-hand side right here cannot be this simple anymore. We have to use a library class. Okay? So I'm going to write that line and I'll explain. So we're going to write is, you're going to say array, which is a library class. And there is a static method there, so I can use an array class without instantiating it. The method is called new instance. The name itself suggests very clearly what it's supposed to do. It's going to create a new array object for you, rather than just say that use the new keyword. Right? So new instance over here, you're going to pass two things. Number one will be the type of the array, which I'm going to explain. But the second one is a bit easier about the size. Okay? So I'm going to put the second one first. So the second one there is going to be whatever size it is, it will be just 10. All right? And what about this guy over here? Right? You're going to specify the type of the array. Conceptually, it should be right here. Right? So there are different ways for you to express this. I'll show you two ways. Okay? Approach number one. We know that the current class where you're writing this line is tree node. And you guys learned about the keyword this, right, before. So you can say, for example, this dot get class. That's basically what you saw from before. This dot get class. All right? This dot get class, you can think about the this that we're talking about right here is really referring to the tree node of E, right? The class where we are writing this line. Okay, right here. That's one way to go. Another way to go would be you can simply write down the class name, which is also fine. Think about this is approach number 1. And for approach number 2, I'm sorry, it's going to be a little bit lower there, right? You can simply write down the class name there. You can say this one here, I will try it out for you. I believe it's going to work, but let me write it down. I'll make sure I try. If the second way doesn't work, I'll tell you next time. But I believe that one's working. You can simply say tree node of E. That's really the class type we need. And then this expression here, you can say dot get class. Right? You can do either way. But approach number 1 is guaranteed to work. For number 2, I'll make sure I try for you. Right? And then I will, if it doesn't work, I'll let you know on Thursday. But I believe it's going to work. Right? Nothing about data structure really, but since we're going to do some practical work in Java, this is actually important details for you to know. Since we're going to implement the tree in a generic way, you should really know how to instantiate or to initialize an array in a generic way. All right? Any question about this? Yeah?
If this .get class is already tree node, why do you have to typecast it again at the front?
Because, okay, good question here. It's because if you look at the API for array.new instance over here, if you look at the API, the return type in general is simply just going to be object array. That's what you will see. So that's why we still want to cast it. Yeah. Good question. But as I said, it's a very ugly workaround. It works, but just not intuitive. That's why I kind of spend the time explaining to you guys. Okay. Yeah, go ahead.
So first, solution.
Yeah.
Data and a new object of 10. Doesn't it have a problem in the future if we use it again? Because in the array, it saves static type is object. So I have to check every time instance of and typecasting of it.
The question was, if we create this array as object over here, are we going to run into problem about the typecasting, right? Okay, the answer is no, very briefly speaking. This one here is only a workaround to make sure we can initialize the array so that it can be created at a runtime. Now let's talk about compilation time, right? So let's say later on, if you try to, let's say if I instantiate this to be string, for example, and then if I write a line somewhere to say data, maybe compiler would know as soon as it write this expression here, it's going to be of type string. It will still work. So the only line that we have to somehow compromise is about this line here of creating that at runtime. So all the benefits about generics where you can actually see what's the instantiated type over here and then use the expression accordingly, it will still apply. Okay? Take some time, okay? All right, guys, that's a very important concept about generics. Make sure you catch up, right? Otherwise, you'll get some errors maybe in your assignments. Yeah, go ahead.
In solution number 2, like, why is it necessary to write like tree node e dot get class? Like, is it not sufficient to just write tree node?
That's something I'm gonna try for you guys, maybe to make sure there's I'll try it out and then make sure I can tell you what's the simplest way to write it. Yeah, but at least number 1 will work. I think number 1 might be the simplest one to really understand because you use a keyword this. But if you want to write out the type explicitly, you can also do that. Whether or not you need the E, I'll experiment with that. Okay. Any other questions? Yeah?
Can you explain why data equals new E10?
Explain again?
Why it doesn't work?
You mean this one here?
Yeah, can you explain why that doesn't work?
Well, conceptually, it makes sense. I'm just saying there's no explanation here because if you simply type it out in Java, it's not going to work. So somehow Java compiler would allow you to simply create a new array where the type here is simply non-existing. That wouldn't allow that. So that's why we got to supply that with the object type, which exists. After that, since we want the generic type, so we're going to cast it. It's like a workaround.
Because like you can't make an object array of a generic type variable, so you have to make an object.
Yeah, exactly. That's a workaround. Conceptually, this should be ideally something we should write, ideally. But it's not going to work at the current Java. I don't think they can fix it. Right? So what you got to do is create the object array and then cast that into E here. Okay? But a static type for the array data, like what your fellow student was wondering, the static type for data will still be E. Okay? I'll write it down explicitly. After this creation over here, this is a workaround just for the runtime. Okay, number one. Number two, the static type. And by the way, static type is something you learned from 2030. Static type simply means what kind of method can you actually call on a particular object, right? It depends on its static type. So static type of, for example, here we talk about data, right? Data at some particular index I remains E over here. Doesn't change the objects. That's something you were wondering about. Yeah, question?
Then, Professor, after initializing the data variable, then what is the dynamic type of data?
Dynamic type?
Yeah.
We don't know yet. Because here, even though it's object here, right? Dynamic type is a good question here. Also, for now, it will be object, yes. No, sorry. Got it. I know what you mean. So here, after this initialization, we know that we're going to create an array, let's say of size 10, right? No. 0, 1, and 2, all the way to index 9. In the beginning, there's no dynamic type because all the elements are null. No dynamic type. And let's say now you actually want to say data. Let's say if I somehow instantiate the E to be, let's say, a string. Let's say, when I create a stack, right? When I say data at the index I is going to be, for example, 23, it's going to give me compilation error because the static type for data I, as I said, remain to be E, which is now string. So I cannot do this. So that one guarantees you cannot store arbitrary object type into the array. Okay? Instead, what you can do is you can say data at index I, because now it should be string. I can say maybe store Alan into it. In that way, for example, I can say this one here is going to be Alan. In that way, dynamic type will be string. So it will still work out. All right? It's kind of like a deep question, but I think that's important. All right? So guys, what I just spoke about, dynamic type, static type, make sure you review. It's something I assume you guys know from 2030, right? I might test you on that, right? If you really got trouble understanding this, reach out. I'll be happy to explain. But that's something I assume you guys know, right? Alrighty, so let's now, okay, so this page here, review it and do some experiments and then make sure you can use it in your assignments and other developments. So let's now try to look at how we can construct a tree, okay? Some example code here. Let's see how we can construct that. And the tree I want to construct is as follows. So what I got is I got Agna. Let me just draw that conceptually first. Agna, and then it has two children. We got Elsa, we got Anna. Right, so let's say that's the tree node structure we want to build, or even like a tree, right? Basically, Agna is going to be the root, which has two children. Each one of them is going to have no children, basically. Right? Let's see how we can build that. To start with, we basically are going to create three nodes. We got one here, and one here. We got three nodes over here. So let's create them one by one. So let's say tree node number 1. We got tree node number 2, and we got, let's say, tree node number 3. All three of them. Let's create them. And if I may, I cheat a little bit. I got a diagram here, so I don't have to draw from scratch. So I'm going to create three nodes. One here, and one already here, and one here. Okay, the first one is going to be the root. And let me just make sure I got some matching color over here. Okay. So Agna, let me just make it green. Of course, after all these three creations, they are not really connected just yet. The way we're going to build a tree node is very similar to how we build a singly linked node or doubly linked node, very similar. And then I got one here, okay, right here. And that one there is going to be pink. And I got another one here that will be orange. Okay, right here. All right, we got three nodes over here after each of these three lines. And then for elements, we got Agna, Elsa, and Anna, right? Let's put it here. So we got Agna will be the element for the first node. And then we got Elsa, which will be the element for the second node. Elsa right here. And also we got Anna, which will be right here. Okay. One thing that's very important for you to see right away. Okay. Remember we talked about the length of the array, which will be 10, 10, and 10. Right? So just by inquiring about the length of the array, it's not going to give you much information about whether a node is internal or external. So you want to think about NOC. I'm going to separate that. So for example, in the beginning, NOC would just be 0. And for this one here, NOC will be also 0. And for this one here, number of children will also be 0 in the beginning. Right? We haven't built any connection just yet. So let's now try to build some connection here. So let me call this one here 1 and 2. Okay, I got 1 here and 2 here. Number 1, we're going to add a child. Okay, so you can look at the source code I made available to you on the lecture site that shows you how you can add a child. Basically, just add one element to the array and then increment the counter. That's basically what we're going to do. So after number 1, we're going to put Elsa into, oh, sorry, just before that, we also got references, right? So this one here is Agna, right here. And also we got Elsa here. And also we got Anna right here, all right? Okay, so now we got references, so we can refer to them. So the first one here, we're going to say Agna, the add child into Elsa. That means we're going to put whatever that is stored in Elsa into index 0, right? That's what we're going to do. So this will be step number 1. As soon as we do that, we're going to update NOC into 1. So now we got one child for that particular object, right? So that's why you want to really watch out to see how NOC is different from the length of the array, okay? And for step number 2, we do something similar. We're now going to add Anna into as a second child. So index 1 is now going to point to wherever Anna is pointing to. So that's step number 2. And we're going to further increment NOC from 1 to 2. So now if you look at the NOC for these 3 objects, you can see this Agna tree node object is no longer external. It's now internal. We got at least one child. And for Elsa and Anna, they remain to be external because the number of children counter here is 0 for both. Okay. One more thing to show, the link should be somehow symmetric, for example, right? You can see here we're just setting up the child references. But what about parents, right? By default, we'll simply get the parents just be null by default, right? When you first create a node. But we just need to make sure if Elsa is one of the children of Agna, we want to make sure the parents of Elsa is set to Agna symmetrically, right? So that's why we got these 2 lines. Okay, I'm going to show to you. So think about number 3 and number 4 right here. Number 3 and number 4. Okay, for number 3, Elsa that set parents Agna. So that means the parent, rather than pointing to null, is now going to point to this node right here, right? So this will be step number 3. And for step number 4, we do the same thing for Anna. So the parents, rather than pointing to null, is now going to point to this object here, number 4. So that will be how you construct a tree node structure for this simple tree here. Right? Yeah.
We add another constructor that takes a second argument to set the parent at the same time.
Yeah, you may. Yeah, so here you're just creating, for example, here, just the content, like an element of the node. If you like in the singly linked node, maybe you can have another second argument which will set the parents. You can do that too. Or you can add another argument which will take the list of children if you want to. It's kind of up to you, really. Yeah. All right, let me say one more thing. So given this particular tree structure here, let's now talk a little bit about aliasing. All right, aliasing is also important. So I'm going to put it here. Aliasing. Okay, I'm just going to write it out directly. You can think about it, how that will correspond to the diagram. First of all, I will start with Elsa. Apparently, Elsa is actually pointing to this particular object here, right? Let me just do that. So Elsa is really corresponding to this particular object. Now, I want to see some example path to really get to Elsa. Okay? One way would be, for example, you can say, I can start with the parents. I can say Agna, the parents, and I can say get children, which is going to give me the array of child nodes, right? I know that Elsa exists as the first child at index 0. So I can go to index 0. All right, so that's the second way. Or I can go for another way if I want to. For example, for number 3, you can think about why it will work. I can say something like Elsa, for example, dot get parents dot get children at index 0. That one also works, right? If you think about it, it just makes sense for the diagram, all right? Of course, there are many other ways to say the same thing, but I just want to give you some example. So aliasing is also very important whenever you got link structure. But now we talk about nonlinear link structure, so that's even more important. Okay. All right, any question about constructing some basic tree? Any question here? Good. And I would suggest we take a look at 2 recursive algorithms about how we can calculate something recursively on the tree. Okay, let's now talk about them. Let's talk about the depth and also heights, these 2. Okay. Let's go one by one. If I go back to the slides, so we are done with slide 14 about walking you through the structure. And also about the, okay, this one is fine. We talk about them. And also, that's the example code we just talked about, right? How you can build some tree structure with the parents and with the children. And of course, if you want some more complicated tree with more levels, you would just do something very similar. Okay, let's talk about 2 problems here. I want to compute the heights and depth of the input. So if you look at the slide, it'll be slide number 17. So that will be the example code I'm going to show to you. I just want you to see what we are going to talk about. I'll switch to iPad once I walk you through. So we're going to see how we can define the Java code. You can see Java code doesn't contain many lines, only a few lines, but we're going to see how it works. So the depth and also some JUnit test cases. And also this is something I want to show you as well. So there are many times when you want to trace the code for recursive algorithm on the tree, you don't necessarily have to use a stack or maybe like a tree, recursion tree that was talked about earlier, like a split array. You can use what I call the unfolding process, which I'll show to you. That one might work too. You just got different techniques that you can use in your toolbox. So that's about the depth. And also we're going to talk about the heights as well, right? So, and then we got some Java code here, which I'll go over with you. And also we got the JUnit test case and also some unfolding tracing, okay? So all the way until slide 22. That's what I'm going to talk about in the next, hopefully, 10 to 15 minutes. Okay. Let's now switch. Okay, stare at this code for one moment. And remember, when we talk about depth versus height, depth is only for a node. Height is actually for some tree. Okay, let's look at this one here. Take a look for 1 minute. Just 1 moment. Okay. Okay. Okay, at least you got some idea. All right, let's now talk about some structure of the code first, and then we'll trace. Okay. Number one, let's convince ourselves it's recursive. Depth over here. Oh, let me use a different color. Depth over here, and it's calling itself. Good. All right. And then we got some base case over here to say if some condition is satisfied, we return. And then we say recursive case, if it is not the base case, we're going to return some operation with the recursive call return value. That's kind of match what we said earlier about recursion, right? But now the target is not an array anymore. The target of this recursive method here is a tree node. As you can see, the input here is n right here. All right? So I'm going to say this one here. So the input over here, the most intuitive way to understand it, and also very accurate, is it's basically the root of some subtree. For example, if I give you Vanessa over here, that means I want to compute the depth for Vanessa. Of course, Vanessa herself is the root of some subtree, right? And if I give you David over here, that means I want to compute the depth of David, the node. And David apparently will be the base case, because we said that in this case, in order for David to get to the root of the tree, it would just be 0, right? So that's something you want to watch out for. All right, let's now take a look. So we say that if the node get parents is equal to null, apparently David here has no parents. It's the root already. In that way, the depth will be just 0. That's by definition. The depth of the root will just be 0. That's the definition. The depth of the root of the entire tree is 0. Okay, what about the recursive part? That one's interesting. Okay, that one is to say, let's say I'm given, for example, the one I'm going to talk about is Vanessa, right? That's what I want to talk about. Okay. If I want to know what is the depth of Vanessa, that's what I'm given. But that problem there is too complicated for me, because Vanessa is very far from the root. I want to somehow say, I only know that there is one single edge for Vanessa to go to her parents. That edge there is 1, which corresponds to this one right here. And then, for the rest of the ancestor path, I can say that they are the strictly smaller problem, which I'm going to leave to recursive call. So you can think about this is a strictly smaller problem. For computing the depth of Vanessa. When you think about the purple one, I just highlight the rest of the ancestor path. All right? So that's really here. Okay, so this one here is really about the depth of Vanessa's parents. So this is saying, if I want to know the depth for Vanessa, I can just say, give me the depth for Vanessa's parents, and then whatever the value is from the recursive call, plus 1. That's the recursive thinking we need from you. That's the simplest case I can give to you at this point. All right, any question about this like a conceptual walkthrough? We're going to trace it, of course. Okay. And if you look at the example code, I actually gave you many different options over here. You can really go over them. You can see for the depth method here, I can call David, I can call Ernesto, all the different nodes. And they might just return different result right here, right? So the one I want to trace with you is this one here, Vanessa, right here. Okay. Specifically, let's look at the depth right here. Okay, let's see how we can somehow use the definition for the recursion and then try to see how we can actually trace it. And the unfolding process is not going to be just like a unique tool just for this. Later on, when we talk about the running time for merge sort and quick sort, we're going to use something very similar. Okay, so you're really warming up also for later algorithm. Okay, let's see this. Let's now take a look at, so we want to say the depth of Vanessa right here, right? By definition, because I know Vanessa.getParents, oh, sorry. There we go. So first of all, I need to check to see whether it's a base case, right? So Vanessa.getParents is not equal to null, right? Apparently it got Elsa here. So it should not be a base case. So by definition, it should be returning this expression here. So it should be 1 plus, okay, the depth of Vanessa's parents, which will be Elsa. All right, I'll pause for one moment here and make sure everybody can somehow follow, right? The reason that I can go from this expression here to here is because, number one, Vanessa here, .getParents is going to fail this base case check. So it's not a base case. So I don't return 0 just yet. So I got to go to the else part. In that way, it's going to be 1 plus the depth of Vanessa's parents, which will be Elsa. All right? So you can think about right here. So we got this link. Right here, right? You can see the 1 here is really corresponding to the 1 here. Okay? Let's now try to unfold. How do I calculate the depth of Elsa? Similar. So we know that the .getParents for Elsa is going to be quiz, also not null, right? Not equal to null. So that means it's actually going to give me something like this. So I still got a 1 plus from before, but now I'm just going to say, by definition, Elsa is going to be 1 plus the depth of her parents, which I'm going to use here. The depth of, and we know that it's quiz. And think about the orange one here is really calculating this particular parent link. That's what we're doing. Right? Okay, we're getting there. And now I want to recursively calculate what's the depth of quiz. Similar, right? Okay, let's now do that. So I still got what I had before, 1 plus, and then 1 plus, and let me say, so depth of quiz, I know that quiz.getParents also is not equal to null. I still can get to David. .getParents also not equal to null. Okay, so I can say here 1 plus the depth. Quiz parents will be David, right? And let me use a different color here. So that one there is going to be the depth of David. Okay, we're almost there. You can think about the 1 here is really calculating this particular edge right here, right? You can see so far we got 1, also we got 1, and also we got 1, right? We got 3. What will be the depth of David? By definition, David.getParents is equal to null. That's the root. That's going to return 0, right? So now you can see all the unfolding process is going to terminate when we calculate the depth of David, which makes sense because that's a base case. Now, if you do the math, 1 plus 1 plus 1 plus 0 is going to be 3. So finally, the answer will just be 3. That tells you in order for Vanessa to get to the root, which is the definition for depth, it's going to be 1 plus 1 plus 1. All right? So this example here, simple, but I think it really tells you many things. Number one, how you can think about base case versus recursive cases if you try to define algorithm on the tree. That's number one. Number two, and given different input node here, that simply means you're talking about different part of the tree. So after going over this example here, you may want to try it out to really trace, for example, this one here, and also Peter, for example, here. Just give you some example. You should really try to trace by yourself too. right? And also to see the unfolding process here, okay, right here. All right, any question? Good. I will make a suggestion here. I'll take a short break. However, there is another algorithm here, which I will definitely go over with you, but I would like you guys to maybe digest a little bit about this depth before Thursday. And on Thursday, I'm going to start with another algorithm, which is about how to compute the heights recursively. That one, they're slightly more complicated than depth. So maybe study this one here before Thursday. If you can look at the code here, just to understand a little bit, that will be very nice. So when I walk it over on Thursday as the first thing, you will also be able to understand. So what I want to do after the break is, why don't we start with binary trees a little bit, okay? There's some mathematical things I would like to mention maybe right after the break. I think that might be nicer. All right, let's now take a short break and also take attendance. All right, so as I said earlier, so please look at the heights. Before next Thursday, we're going to go over that very quickly on Thursday. But for now, I'm just going to, I'll go over this maybe again. Okay, let's talk about binary tree, right? We can move on. We'll get about 10 minutes. Let's see what we can do. For binary tree, it's very similar, but now we have some constraint. In some ways, simpler than general tree. Now, when we branch out, you cannot say you got, well, rather than having a list of children, in some way you got only two options, either left tree or right tree. That's something we'll see, okay? We got some definition here, but this is really important, right? That's the most important thing you got to remember. In a binary tree, it's an order tree. You guys remember what an order tree is? That means that the order of the children matters. Each node has at most two children. Can be no child, can be 0, can be 1 child, or it can be 2 children. And for the children, we're going to call them left and right. All right, let's now do some little bit quick visual sketch, okay, very quickly. The way we're going to visualize the base cases will be just the same. For that one, I'll refer you to what we said earlier over here, right? For the base cases, you guys can take a look at case number 0 and case number 1, the same. For that one, I'm going to list them there, but the detail, you can just look back, the same, okay? So I'm going to say for binary tree, we got case number 1, case number 0. Case 0, empty tree, the same as before. And also we got case 1, it would be a singleton tree, also the same as before. Okay, right here. And what about the more complicated case? Case number 2. When you have more than 1 nodes, 2 or more, basically. All right, so this is how you visualize a binary tree in general. You have the root somewhere, okay, at the top, basically, right? And then the way to visualize this is very simple. There will be a reference called the left. There will be the other reference called the right. Because the order really matters, you got to really make sure you go to the left or go to the right accordingly. And then the left child is going to be a tree node. The right child is also going to be a tree node. And we talk about recursive structure here. So here you can think about this will be the subtree for rooted at the left child. This will be the subtree rooted at the right child. Oh, sorry. Right here. Okay, like that. Okay, we got 2 subtrees basically. And normally we call this the left subtree. LST, left subtree. And here we call that the right subtree. RST, right? That's what we're going to know. So that means at each level, you can branch out at most 2 times. All right. The last thing I would like to talk about is something to get you guys prepared and also review a little bit about math before Thursday, right? Do you guys remember something called geometric sequence? Oh yeah? Okay, do you know what the formula is? Okay, if you say no, that's great. So let's now talk about it. All right? There will be no data sheets for the exam. So if you forget about the formula, this is how you would derive it. That's how I do it as well. I don't really memorize the formula. So if I really need a formula, I can always derive it. Okay, let's take about 6 minutes to see that. Okay, geometrical sequence goes like this. For example, I got 1 plus 2 plus 4 plus 8 plus 16 plus all the way to 1024. That's one example. Okay. One thing is, this is a geometrical sequence because you can think about this is something called the initial term, I, the first term. And there is so-called a common factor R. So if I go from first term into the second term, multiply by 2. If I go from the second term to the third term, also multiply by 2. That's what a common factor really means. Also, we got something called the number of terms. Guys, before I explain this, do you know what k is in this sequence over here? How many terms do we have in total? How many? Spence, go ahead. 11? Oh, that's great. I was expecting somebody to say 10. Okay, good. Okay, let's see why. Easy. You guys can see this one here is 2 to the power of 0, right? This one here, 2 to the power of 1, 2 to the power of 2, all the way to 2 to the power of 10. So we're basically counting from 0 all the way to 10. So we got 11 terms, all right? So here we got k equals 11, number of terms. All right, just one example here. And now we want to see if I want you to calculate what's the sum of all the terms in this particular sequence. Let's see what the formula is. All right. Let's now make it mathematical. Okay. So let's say I got sequence like a geometrical sequence k with k terms. That one is going to be I got the initial term I plus I multiplied by the common factor plus I multiplied by another common factor. So that will become exponent 2 plus I times r to the power 3 plus all the way to what will be the last term if I got k? Anybody? R to the power of k plus 1 minus 1. All right, guys, be careful because if you think about this guy here, it's really about I times r to the power 0. That would make sense, right? Okay, precision. All right, watch out. This is how now the critical step is how do we know the sum? Okay, you guys may have seen this in the high school or maybe in the calculus course. I don't know. I can now try to do the following. I can say I want to multiply s of sk here just by another r, the common factor. That means I times r will be I times r right here. I times r times another r will be I times r squared. And this one here times r will be I times r to the power 3 plus etc. I will definitely get this one here from the previous term. And I should get another term, right? Because this term here times r will be I times r to the power of k. All right, be careful. So think about this is the last term, and this is the last term. Okay. And now here comes the magic. You can see that this part here are exactly the same. Agree? Okay. So what I can do is I can now say, I would say r times sk minus sk, which I know would be simply factor out r minus 1 times sk, which will be equal to, I'm basically saying subtract, I'm basically saying this one here minus this one here. So this part is totally gone. I will get only this part here minus this. I times r to the power of k minus I times r to the power 0. Right? And I'm pretty sure you have no trouble if I try to do this. Well, let me just say I here, right? Just a little bit simpler. Okay. That would be basically I times r to the power of k minus 1. All right, so basically what we got is I try to do this, and then I got this. But my goal really is to, I think this will be better. I want to get this, and then I got this. Right, what will be sk? So now I can finally say sk will just be equal to basically this guy here divided by this, right? I times r to the power of k minus 1, r minus 1. That's the general formula. Given arbitrary r and also I. Why am I talking about this? Because in the case of binary tree, we have to think about some special value. Let me mention that. Give me 30 seconds, and then we are done for today. What you want to think about is, in the case of binary tree, which we have to dive deep into next time. For binary tree, we have some special value. R, the common factor is going to be 2. And we start with a single root. So that means the initial node is just one node, right? And also the I will just be 1. So the 2 over here is about whenever you got any node, you can only branch out at most twice, right? That's about a branch out, number 1 and number 2. And also for this one here, it's about a root. There's always just single root that you have. Quick question. If I got these two special numbers already, what will be the final answer for sk? Right? So now that one there, I'm not going to trouble you. R minus 1, 2 minus 1. So we don't need to worry about anything about denominator. I here will just be 1. Awesome. All we got will be r to the power of k minus 1. Sk will be r to the power of k minus 1. As we'll see later, the k over here will just correspond to the depth of, I would say a little bit more informally, bottom node. All right, so before Thursday, please review this formula here. I will assume you guys know about that formula. And also take a look at the depth and also heights, and then we'll go from there. Thank you.